We start by examining how a random variable has its PMF or PDF altered by learning that some conditioning event has occurred. For example, you could have n be the number of bytes in an email, and a conditioning event might be the event I that the email has an image. On the other hand, we might simply learn that the email is big, that it has more than 100,000 bytes. Both of the events I, or the event that the file size is more than 100,000 bytes, tell us that the email is big. To describe the conditioning of a random variable, we start with the conditional CDF. The idea here is that before we do an experiment, X has a CDF. After we learn that event B has occurred, X has a new CDF, and we call it the CDF of X given B, and it's simply the conditional probability that X is less than or equal to X, given that B has occurred. Everything we've said about CDFs being difficult to use still applies to the conditional CDF of X given B. So when X is discrete, it's much more convenient and easier to work with a conditional PMF of X given B. And just as we had before, an original PMF of X, which simply tells us the probability X equals X. We now have the conditional PMF of X given B, which tells us the probability X equals X given the conditioning event B. And I just have to add a comment here that effectively, the way to think about these situations is that the notation is really the same. We have a superscript P for the PMF, and then we have a subscript, which is the name of the random variable, and then we have a dummy value, X. And the idea here is that random variable X becomes random variable X given B when you learn that B has occurred. You can think of X given B as a new random variable with PMF X given B of dummy variable X. Similarly, for a continuous random variable X, we can think of X given B as a new random variable with a conditional CDF of X given B. Once we have this conditional CDF, we can think about what's the density function associated with that random variable. And in that case, we define the conditional PDF simply as the derivative of the conditional CDF. When we introduce conditional random variables, defining the density as the derivative of a CDF was somewhat confusing, and perhaps it still is here. However, we'll see that conditional PDFs are, once again, very easy to work with. When B is shorthand for the event that X belongs to the region B, this theorem gives us simple formulas for calculating the conditional PMF and conditional PDF. When X is discrete, the conditional PMF of X given B of X tells us the probability X equals little x given B, and this is simply by the definition of conditional probability, probably X equals little x and B over P of B. And when we use the fact that B is shorthand for X belongs to B, we have this is the probability X equals little x and X belongs to B over the probability of B. And now we see in the numerator that there's sort of two possibilities. Either the element little x is in the set B, in which case this probability is just probably x equals x, or little x does not belong to the set B, and in this case this joint event has zero probability, because if x doesn't belong to b, then you can't have x equals little x and x belongs to b. The consequence is that the numerator is either the PMF of x when x belongs to b, or it's simply zero, and we obtain our theorem. The same logic holds for the case when x is continuous, and in this case we have that the conditional PMF of x given b times dx we think of as the probability x is in the interval x plus dx given b, and this is equal to and the event that x belongs to b over the probability of b. And now we see that if little x belongs to b, or more specifically, if the interval from x to x plus dx, this infinitesimal interval, belongs to b, then this probability, the numerator, is simply the probability that x is in this infinitesimal interval, which is the conditional PDF of x times dx. And the denominator always stays the same. And the result here is that we obtain the equivalent theorem for continuous random variables, that the continuous, the PDF of x given b is the PDF of x divided by p of b when x belongs to b and zero otherwise. Effectively, in both cases, what we're doing is we're taking values of x that belong to the set B and scaling up either the PMF or the density function by 1 over p of b. And the consequence of this is that the conditional PMF sums to 1 over the set B, and the conditional PDF integrates to 1 over the set B. This may seem abstract, but actually it's pretty simple. In fact, it's simple enough that we can jump ahead to the end of this section and take the quiz. You'll see that, in fact, that there is a quiz. This is section 7.1, and this is quiz 7.1b. In chapters like this one, where we use the section to describe both continuous and discrete things, we'll sometimes have an A quiz that's discrete and a B quiz that's continuous. So in this quiz, y is a continuous 0, 10 uniform random variable. That means it has a uniform PDF from 0 to 10 with value 1/10. And now we can do step A, where we calculate the probability y is less than or equal to 6. That's equal to the integral minus infinity to 6 of the PDF of y. And that's equal to the integral from 0 to 6 of 1/10 dy. And it's exactly 0.6, as you would expect. Of course, this is just a warm-up question. You learned how to calculate this probability a long time ago, but we want to use that in calculating the conditional PDF of y, given this conditioning event that y is less than or equal to 6. We recall that our theorem says that the conditional PDF of y given b of y is the PDF of y divided by p of b for y belonging to b and 0 otherwise. In this case, the conditioning event b is that y is less than or equal to 6, and the conditional PDF of y given y is less than or equal to 6 is equal to the PDF of y all over the probability y is less than or equal to 6 given y is less than or equal to 6. and 0 otherwise. And this is equal to 0.1 divided by 0.6, i.e. 1/6, for 0 less than or equal to y less than or equal to 6, and 0 otherwise. It's worth noting here that the condition y less than or equal to 6 became two conditions in the next step, y greater than or equal to 0 and y less than or equal to 6. The reason is because the first condition is given, but the second condition comes from the PDF of y being 0 for y less than or equal to 0. Parts C and D are almost the same. The only difference is now we're going to condition on y being greater than 8. So y will be over here in the interval from 8 to 10. And as you can see in the solution that follows, the conditional PDF of y given y is greater than 8 will be a uniform random variable from 8 to 10. So this slide includes the details for step C and for step D for the conditioning y greater than 8. So far we've learned how some extra information about a random variable, say y is less than or equal to 6, gives us a new distribution, a PMF or PDF for that random variable. However, in this theorem, we really use conditional distributions in the opposite way. In this case, we have a collection of conditional PMFs, P of x given B1 of x, P of x given B2 of x, up to say P of x given B sub m of x. And this collection, B1 through Bm, has to form a partition. The idea here is the following, that B1 and B2 and so on describe kind of different modes of operation of a system. And under mode 1, the PMF of x is the conditional PMF of x given B1. And under mode 2, x has PMF given by the conditional PMF of x given B2, and there may be an arbitrary number m of such possible modes and different distributions, conditional distributions to describe x. The same logic also holds when x is continuous. In this case, for each mode of operation bi, x is described by a conditional PDF of x given bi. Now what this theorem says is that we can synthesize the distribution of x, either the PMF or the PDF, by combining the conditional PMFs or the conditional PDFs. In fact, this theorem is nothing new. It's just the law of total probability written with PMFs and conditional PMFs. For example, if x is discrete and A is the event that x equals x, the discrete version of the theorem says that P of A is equal to I equals 1 to m, P of A given BI times the probability of BI. This is just the law of total probability from chapter 1. When x is continuous, we can think about taking the left side of this equality and multiplying by dx, and also by multiplying by dx on the right side. And then we define the event A, that x is in the interval from x to x plus dx. And so on the left side of the continuous case, we have the probability x is in this interval, namely this is P of A. And on the right side, we sum over all possible cases 1 through m, and we have the probability that x is in this interval given B, I, times the probability of BI. just as in the discrete case, this is just a fancy version of the law of total probability using density functions and conditional density functions. The power of the theorem comes from being able to build a distribution for x, a PMF or PDF, from a collection of conditional distributions that describe different possible cases. In this example, we build a model for the life expectancy of a senior citizen by considering two cases. The first case is event H, that the person has high blood pressure, and in this case we model the life expectancy as geometric with parameter p equals 0.1. The second case is the blood pressure of the person is normal, event N, and in this case, X has a geometric PMF with parameter P equal to 0.05. From these words, we have two conditional PMFs. We have the conditional PMF of X given high blood pressure, and this is equal to 1 minus 0.1 to the X minus 1 times 0.1 for X equals 1, 2, 3, and so on, and 0 otherwise. And we also have the conditional PMF of X given normal blood pressure, and this is equal to 1 minus 0.05 to the X minus 1 times 0.05, X equals 1, 2, and so on, and 0 otherwise. And finally, we get some information that allows us to combine these facts. And this information is that 40% of all 70-year-olds have high blood pressure. And when we know that, what this is telling us that the P of H is equal to 0.4, P of N is equal to 0.6, and assuming that there is no case of low blood pressure in the model, then either a person's blood pressure is high or normal, and in that case, Hn is a partition. And we can use the theorem to write that the PMF of X is 0.4 times the PMF of X given high blood pressure plus 0.6 times the PMF of X given normal blood pressure. This next example describes a model for what happens in your cell phone thousands or millions of times per second, depending on the rate at which you're downloading bits from the internet. Associated with each bit is a noisy voltage. When the symbol 0 is transmitted, which corresponds to event B0, X is the Gaussian random variable with expected value minus 5 and standard deviation 2. On the other hand, when a bit 1 is transmitted, that's event B1, X is the Gaussian with expected value 5, positive 5, and standard deviation 2. If the communication process was noiseless, then the standard deviations would be 0. The minus 5 and plus 5 voltages represent the bits 0 and 1. The standard deviation 2 is derived from the signal-to-noise ratio of the communication process. As the SNR goes to infinity, this variance with standard deviation would go to 0. From the problem statement, we have two conditional PDFs. The conditional PDF of X given B0, given that 0 is transmitted, is 1 over square root of 2 pi times 2 squared, where 2 is the standard deviation, e to the minus x minus minus 5 squared over 2 times 2 squared. And so this simplifies to 1 over square root 8 pi e to the minus x plus 5 squared over 8. And in the case of a 1 being transmitted, we have a conditional PDF of x given b1. And this is 1 over 8 pi because the standard deviation is the same, e to the minus x minus 5 squared over 8. And now we can find the PDF of x by combining these two PDFs. Because they're equally probable, they're each weighted by a factor of 1/2. And we obtain 1/2, 1 over square root of 8 pi e to the minus x plus 5 squared over 8 plus e to the minus x minus 5 squared over 8. We know that each of these functions is a bell-shaped curve. This one is centered at x equals minus 5, and this one is centered at x equals 5. If you sketch this PDF, you obtain peaks at minus 5 and 5. The PDF looks like two bell-shaped curves. If my drawing skills are better, these two bell-shaped curves would be identical. Also, it's worth noting that I show in the drawing as if these PDFs go to 0, and in fact they're not exactly 0. They're just really small, like 10 to the minus 4 perhaps, because each one of these PDFs is now 2.5 standard deviations beyond its expected value. Another side note worth mentioning is that this is a classic example of a bimodal PDF. Remember that a random variable has modes, and a mode is where the PDF is maximized. This random variable has modes of 5 and minus 5, and what they really correspond to is modes of operation of the system. There was a mode that corresponded to transmitting a symbol 1, and a mode that corresponded to transmitting symbol 0. And the two peaks represent the distributions under these two different modes. Since my writing's a little sloppy, here is the full solution to the example. This quiz, using a discrete random variable n, which is the number of packets in a web page, is similar to the last two examples. N is either distributed between 1 and 50 if the page has images, or it's between 1 and 5 when the page is just text. And what this quiz does is it synthesizes the PMF of n from the two conditional PMFs. At this point, if you follow the last two examples, you should have no trouble with this quiz.